Hi, my name is Hindi Purohit, and this is my implementation of the RSA algorithm. We begin by taking three inputs. The inputs are limit, precision, and ITR count. The first variable limit would be explained later on in this video. Precision is the number of bits, the bit length of the number that we wish to generate. And ITR count, we are basically using the Miller-Rabin algorithm to test for primality. So we need to determine the number of iterations for the Miller-Rabin algorithm. So we are taking that input and storing it into ITR count variable. This is just for calculating the amount of time that this algorithm takes to generate prime numbers and encrypt and decrypt messages. Then we're calculating the upper and the lower bound. In our case, it's a 16-bit number, so it would be 2 raised to 16 minus 1, and the lower bound would be 2 raised to 15 plus 1. Then we calculate P and Q by using this function, get probable prime. If we navigate to this probable prime function, we see that we are first generating prime numbers. So let's jump to the prime number generator function. This prime number generator function uses Atkins sieve to generate first few prime numbers. We could have also used Eratosthenes sieve in place of Atkins sieve, but since Atkins sieve is the fastest implementation, I'm going to use this sieve. I'm generating various prime numbers using this Atkins sieve. Then going back to this probable prime function, in this particular while loop, I'm generating a random number. This is the implementation of the random number generator function, and using this I'm basically filtering out all the even numbers because even numbers can never be prime. So this is used to generate random numbers and get probable prime. Okay, here. So once the random number has been generated, we need to check whether the number is prime or not. So I'm using the Miller-Rabin test, and before doing the Miller-Rabin test, I need to divide that number by the first few prime numbers that were generated in this prime generator function. Once if a random number can be divided by the prime numbers that were generated using that prime number generator function, then the number is not prime. Otherwise, we need to proceed and check if the number is prime using the Miller-Rabin algorithm. This function basically utilizes this Miller-Rabin algorithm that would test whether a given number is prime or not. And we are also using square and multiply algorithm for modular exponentiation, because otherwise if we use the normal arithmetic to raise a number to a power and then calculate modulus, it would be too expensive in terms of computing and memory resources. So this is the implementation of the square and multiply algorithm. Check if prime. Okay, so if the number is not a prime, it would be filtered out using this if condition, and if the number passes this for loop, we check whether it's a prime or not using this Miller-Rabin test. I'm using around 10 passes of Miller-Rabin test, and if I use 10 passes of the Miller-Rabin test, I get an accuracy of 0.0001%. So there is 0.0001% chances that the number that I generate is not a prime number, which is very, very accurate. Get probable prime. Once we have the probable prime, we return it to the main function. So this is how we calculate P and Q. Once we have P and Q ready, we can calculate N by multiplying the values of P and Q. And then phi n is nothing but the multiplication of P minus 1 and Q minus 1. Similar to the generation of P and Q, we can calculate E, the value of E, using a similar method. We need to pass the limit, the iteration count for the Miller-Ribin algorithm. The numbers discarded is not a necessity. I'm just using it to find out the efficiency of my algorithm. Then this is just the upper and the lower limit, the phi n. This function is used to calculate the private exponent d, the private exponent function. We are using the extended Euclidean algorithm to find out the value of d, which is the private exponent in the RSA algorithm. And yeah, E. One thing about E. E is a random number which is less than phi. So we calculate a random number which is lower than phi n. And since we need a prime number, E and phi n should be coprime. So that makes the execution of this algorithm fast. We don't have to check whether they are coprime or not, because two prime numbers are anyways going to be coprime. And then here we are just printing out all the results that we obtained until now. So let's run this program and check the output. Enter the number of first few prime numbers to be generated. So for example, let's generate prime numbers up to 300. The bit length is 16 and the number of iterations 10. Yeah. So this is our result. We got n as this value, phi n, e, and d. But since the value of d cannot be negative in our case, let's run this program once more. Number to be generated 300, enter the bit length 16, iterations 10. Yep. Okay, so I'll be using these values for our project. The prime numbers, enter the number of first few prime numbers to be generated. That's 300. So before executing the Miller-Ribin test, I am dividing the randomly generated number by all the prime numbers up to 300. If a number can be divided by one of those prime numbers, then it's composite. So just to reduce the computational overhead, I am doing this step, nothing else. This is P, this is Q, N, phi N, E, and T. And it took a total of 135 microseconds to get this result. Thank you.